Good morning, ladies and gentlemen. Welcome, welcome. May I have your attention, please? Thank you. So today we begin Unit 1, Day 1, our prerequisites for AP Calc Bc, and we will be recording, okay? And so once again, you're used to this from last year. Don't be anxious, don't be nervous, but I will be calling on you from time to time, and we'll be exporting these, right? And then we'll be posting them on our Moodle website so that you can access them later for your reference. Let's see how we did with the marker game. But firstly, I'd like to introduce our new student, Brendan. Brendan joins us from Ashwaubenon, and so thank you for making him feel welcome, and I'm so glad you came, not just because he'll be in BC and AB back-to-back, 1A followed by 2A for a double/triple dose for this block schedule / quadruple dose of AP Calculus, so that's pretty sweet, but also because it makes 3 groups of 4. I mean, not that those bother you. Not just sort of a little bit annoying that we didn't have 3 groups of 4, but now we do, and that's awesome. Thank you, Brendan, and welcome. Okay, ladies and gentlemen, let's go ahead and take a look. Thank you to those of you who came and shared your responses. I appreciate that. So it looks like the domain of y equals cotangent of x is a set of all real numbers such that x does not equal 0 plus or minus pi n, because cotangent is cosine over sine, and at x equals 0 plus or minus pi n, we would have a sine value of 0, and we can't have a 0 in the bottom fraction. Absolutely. I'm going to make this a double word R for the set of all reals, except x can't be 0 plus or minus pi n. Awesome. Raise your hand if you had number 1. That's correct. Great work. Number 2. The restricted domain and range pairing of my original sine function creates an inverse sine that is itself a function. I have a new restricted domain for inverse sine of -1 to 1 inclusive. So we have our brackets. Raise your hand if you had number 2 correct. Awesome work, you guys. Number 3 is the same domain, -1 to 1. Raise your hand if you had number 3. Good. And before we take a look at number 4, I just want you to think about the difference of number 2 and number 3. Their domains are exactly the same, and yet their range differs, right? If I put in a value in between -1 and 1 into my inverse sine function, I'm guaranteed to produce an output in between what y values? What's my restricted range for inverse sine? Grace?
Negative pi over 2 to power 2.
Wonderful. Negative pi over 2 to positive pi over 2 inclusive against brackets. Thank you. What's the restricted range of the inverse cosine function in number 3? Be ready. What's the restricted range for the inverse cosine function? Sydney?
0 to pi.
0 to pi. Good. That's my restricted range. Excellent. Thanks. And the inverse tangent function exists for all real inputs x, -3 to infinity. Just make sure that you're using parentheses on your endpoints -infinity to infinity, because they're not actual values, they're just descriptions, and so they always get the parentheses for interval notation. Awesome, thank you. Raise your hand if you had number 4 correct. Great work. Number 5 and 6 are setups for today's discussion. So number 5 and number 6, we'll be looking at sequences, and recall that sequences are just an ordered list of objects or numbers, right? So we're looking at an ordered list of objects and numbers, or in this case, letters. So I hope you had as much fun with that as I did. So here we go. 2, -6. Raise your hand if you had the same blue entries up here. So what was the pattern there? Right? What was the pattern there? Brendan?
Multiply by -3.
Multiply by -3. Good. So anytime we have a constant ratio between successive terms, a constant multiplier, right? We have a specific name for that kind of sequence, and we'll look at that in our activity. Good, thanks. And then Courtney tells me, he swears that that's an E. And so just for my sake, I'm going to put that there, 3 groups of 4. Awesome. You complete me. So we'll go ahead and 1, 2, 3, 4, 5, 6, 7, 8, 9. Raise your hand if you figured that one out too. That's pretty sweet. Awesome. Great. What questions do you guys have on today's Bellwork? Okay. So let's take care of our housekeeping. So we do need a stapler. We'll send that around. And I'll pause the recording while we do our check. Okay, so what's new for Calc Bc? Well, as you know, right, we're going to be dealing with vectors. We're going to be dealing with parametric functions. We're going to be dealing with polar equations. And so this prerequisite unit is meant at reminding you about kind of these topics that we haven't seen at all in AB, right? So it's been a couple year break from some of these key topics that are now built upon and applying the calculus concepts to in the AP Calculus BC course, right? And so we're going to spend unit 1 kind of refreshing our memory about these things, right, in order to go ahead and look at some more applications in the BC course. To that end, we're going to look at sequences today. So your Bellwork was a kickoff. Today's sequences activity, we've got stamped eligible items. Just take a minute and put a little circle around those. 3B, 8B, 13B, 14C, and 19 for a grand total possible of 5 activity stamps today. Thank you for working well together, talking it out. I sincerely believe that by discussing this mathematical content, you'll not only understand it better, but you're going to remember it longer. When you guys all agree, go ahead and raise your hand and I'll come to you. And again, thanks for making Brandon welcome. I'm going to go ahead and pause the recording so that we can get started on your activity. And then we do have a surprise fire drill at like 9:35, so I want to make sure that we come back together at like 9:25 so that we have time to complete our closure. Okay, so we will be doing our closure, and you can see that on your note sheet, the last slide. So let's go ahead and without further ado, get started. Okay, ladies and gentlemen, so out of today's activity, I wanted to remind you about those key formulas for arithmetic and geometric sequences. We can express the formula for an arithmetic sequence in 2 different ways, explicitly or recursively. In just a minute, I'm going to have you down, come up to the board, and I'm going to have you write with the correct notation what the explicit formula would be there for number 1. I'm going to give you a kickstart for number 2. Number 3, an explicit for a geometric sequence with first term G sub n and constant ratio r, and then recursive. So what I mean by a kickstart is you're going to come and do number 1 in its entirety. For number 2, I'm just going to go ahead and pretend that we're given a value, some arbitrary constant k. My start value is 1. Let's let it equal k, and then you can complete that recursive part right there. See what I'm saying? Same for the geometric. I'll pretend that we're given first term, call it G sub 1 equals k. Okay. Vivian, will you come down and complete number 1, please? Thank you. Danny, will you go ahead and complete number 2, please? And Marissa, you want to come and do number 3, please? Thank you.
Oh, our thought. Where does it go below? I don't know. Your thoughts are really good. Thank you.
Nice effort. Kylie, do you want to go ahead and complete some form?
I don't know what your church is either.
Awesome. Thank you, ladies and gentlemen, for sharing your responses. Let's go ahead and take a look at our closer. Number one, I can get the 50th term, right? The 50th term easily by plugging in n equals 50 to my explicit formula and evaluating. I need to know my first term a sub 1, I need to know my constant difference d, and then I'll plug in the term number for n and work it out. Nice job. Raise your hand if you have the general form for number one, explicit arithmetic. Good job. Number two, we need a start value, right? For our recursively defined sequence, we need a start value and then a rule that's used to get the current term based on the previous term. What do? We look at the previous term's value and we simply add my constant difference number to it, and that'll create, right? That'll create my current term. How do I get the next term? I look at the current term and I add my difference to it, add my difference to it, add my difference to it. That's the pattern. Nice job. Raise your hand if you get number two correct. That's awesome work. Geometric, we're not adding a constant difference between successive terms, we're multiplying by some constant ratio, right, between successive terms. So g sub 1 is my first term, and then I'm going to multiply it by that constant multiplier, r, to the n minus 1 to account for that first term. Nice job, you guys. So raise your hand if you're number 3. That's correct. And that is an exponent, right? That is an exponent. And then number 4, we need that starting value. To get the next term, we'll look at the current and we'll multiply it by my r value, right? To get the current term, I looked at the previous and multiplied by r value. Nice job. Raise your hand if you had number 4. Great work, ladies and gentlemen. So we've got our OTL number B. Since I'm setting up for our Unit 1 prerequisite unit, we're going to finish the sequence activity. I think you guys all managed to take care of that. Our textbook, we've got a fairly short assignment today. It comes from 2 sections, a little bit more trig, and then some sequences work on page 449 out of a whopping 12. I'm going to go ahead and pause and load our recording to our Moodle site now. Great work today.